Hello everybody, I hope all of you are doing well. So today we are going to solve a problem on rigid body vibration or for small oscillatory motion. Okay, so here is a problem, and I have the figure that is drawn right down. Okay, as you can see. So in this particular problem I have a spool. Okay, so this is the spool S. The subscript for the spool is going to be S for us. Then there is a block here, so this is a block. I guess I don't want to write on the block. Okay, so this is the block. Let's call it as B. Okay, and then the blue color thing, as you can see, is the cable. Okay, cable is C. Okay, so you're told that this spool is rolling without slip on a flat horizontal surface. Okay, so spool rolls without slip. On flat ground. Okay, let's say that the mass of the spool is m suffix s. Mass of the block is m suffix b. Okay, and the cables and pulleys are massless, negligible mass. Negligible mass, and let's say that the inner and outer radius of the spool are given to us. Okay, so the outer radius is going to be r0. Let's say that is that distance here, or r. That's going to be r, and then this distance here, let's call that as a distance rho. Okay, let's make sure that this is indeed straight. Okay, that looks pretty straight. Okay, so that is going to be called as rho. Okay, so inner and outer radius are given to us. Radius of the spool is rho, and then the outer radius of the spool is capital R. Okay, damping coefficients are given to us C2 and then C1. I have a spring that is attached. As you can see, they're attached to the wall at one end and then the spool on the other end. Then likewise for the block as well. Okay, they have a spring of stiffness K2 and the damping element C2. Okay, what do I need to do for small motions? Obtain the equation of motion. Equation of motion for the system. For the system shown. Okay, so this is the problem that we need to solve. Okay, all right. So in these kinds of problems, what are my typical steps? Okay, so here are my typical steps. So I look at the problem and I immediately realize there is rolling without slip, which means that I have to do some spool kinematics. Okay, then once I do spool kinematics, I realize, okay, hey, there is and there is the cable is wrapped within the inner groove of the spool. That's something I want to make a note of here. Okay, note that. Let me write this down here very quickly. Note that cable is wound along the inner groove. Okay, inner groove of the spool. Okay, and you can assume the cable length, total cable length, to be a constant. Is a constant. Okay, so that's an assumption that one can make, and we know that it's rolling without slip, so there is no kinetic friction and so on. Okay, drag and all these things are also neglected. Okay, so whenever I look at a problem like this, I say, okay, there's spool kinematics involved. Then there's a cable pulley system, so there is cable and pulley kinematics involved. Then after I'm done with that, I go ahead and I start off by saying, okay, find the number of degrees of freedom involved. Once I have the number of degrees of freedom involved, then I realize, okay, hey, you need to start off with the sign convention for the coordinate systems, okay, or the degrees of freedom. And once I do that, free body diagrams, kinetic diagrams, and we are home and dry. Okay, all right. So here is what I'm going to be saying. This is my solution steps. Okay, so solution. What are the steps that I'm going to be taking? So first things first is look at spool kinematics. Okay, then the second thing is look at cable plus pulley kinematics. Then the third thing is look at degrees of freedom. And set up a coordinate frame and so on. Okay, positive sign convention. Okay, then my next step is free body diagrams of the springs and the dampers. Okay, and the last step is the kinematics for the problem. Okay, rigid body kinematics. All right, so these are the different steps in my problem. Okay, so once I have these, then the first thing is typically I do the kinematics is because the kinematics lets me get more confident in terms of how to solve the problem, and it's obviously good to get the kinematics done first. Okay, because you're going to need that information to do the kinetics. There are some people who will just directly start drawing the free body diagrams, but that is not my style. Okay, all right, so let's look at what's going to be happening here. I'm going to take the spool and start doing some kinematics on that. You already have seen this many times in the past, so this is not something new, okay, in my previous problems and so on. So let us look at spool kinematics. Okay, and in this we are told that it's rolling without slip. Okay, so bring that guy here, and we need to start labeling some things and so on. So I'm going to cut that off. I'm going to cut that off as well. Okay, so let's start labeling these points. Okay, so let me call this as point C. This is point D on the ground. This is the point G, which is the center of mass. Okay, now look at this very carefully. I have point P on the cable and point P on the spool. Okay, so they are coincident points, and then let me call this as the point A. Okay, where the spring was attached, right? And if you want, you can cut this off. I don't need this guy here. Let me remove that. Okay, so this is the spool with the cable involved. I don't really care. Maybe let's have the cable, a little bit of the cable, which is shown here. Set up a coordinate frame. That's the first thing, right? So I, J, K direction for me. This is J, then this is I, and this is K. Okay, then I'm going to start assuming certain things. I'm going to say that the spool is rolling in the clockwise direction. Okay, I'm going to say this is alpha S, and also angular velocity is in the clockwise direction. I don't know at this point in time. I'm just assuming it to be that way. Okay, so assume alpha S is minus alpha S in the K direction, and then omega S is minus omega S in the K direction. Okay, so that's something that we have taken care of. Okay, then we also know that it's rolling without slip. Okay, so rolling without slip, which implies the following. This shows that the acceleration of C/D in the tangential direction is equal to 0. What is my tangential direction? If I set up the coordinate frame here, so this is going to be the tangential direction. This is going to be my normal direction, if you want to write it that way. This is the normal direction. Okay, And so at that point in time, the normal and the tangential are coincident with I and j. So at that instant, this is something you can write. T is coincident with I, and then n is coincident with j. Okay, so this tells me that acceleration of c in the tangential direction is the same as the acceleration of d in the tangential direction, which is equal to 0 because the ground is fixed. Okay, so since the ground is fixed, we have this, and so I can write the acceleration of c is 0 in the I direction. Okay, so this is essentially in the I direction, as you can see there. Okay, plus something in the j direction, which I don't really care about. Okay, then once I do that, we also further know that the spool should not lift off of the ground. Okay, so spool does not lift off of the ground, which implies that the acceleration of the spool is going to have only a component in the direction parallel to the ground, which is the I direction in this case. Okay, then I can make use of the fact that, okay, acceleration of g is acceleration of c, alpha of the spool crossed with r g slash c, omega square of the spool times r g slash c. Then these relative terms which do not make an appearance in this problem, v g slash c relative, okay, they can be discarded. This is all gone. And if I do the substitutions, this is ag in the I direction, this is 0I, and something in the j direction. Then this is minus alpha of the spool k. Position vector from C to G, sitting at the point C, looking at the point G, is R in the j direction. Okay, so this is going to be Rj, and minus omega square of the spool times Rj. Okay, so which means comparing, looking at the I terms, I'm going to get Ag is equal to k cross j is minus I, minus and minus becomes a plus, so this is R times alpha of the spool. If I look at the j direction, of course, I'll end up 0 n ACN minus or omega s square. So from this, essentially the only information that I need is acceleration of g is r times alpha s in the I direction, acceleration of c is 0I, and r times omega s square in the j direction, the centripetal acceleration, pulling it away from the point that is in contact with the ground. Okay, so once I have this, then I want to write a couple more things. Okay, so look at this, and I can also do the same thing for the velocity analysis. Okay, so velocity analysis, if I do this, in a sense, I can say that velocity of c slash d is equal to 0, roll without slip. Okay, which gives me that velocity of c is equal to velocity of d is equal to 0. Okay, so this doesn't a very good thing for me because d is fixed. Okay, is on fixed ground. Okay, and then once I have this, I can write the following. So then velocity of g is velocity of c omega of the spool crossed with position vector, right, rg slash c, and then the relative velocity term is going to vanish, as you know. Okay, so this is gone, this is also gone, which means if I do the substitutions, I can write this very quickly as velocity of g is going to be r times omega spool in the I direction. If you do the computations, you'll end up getting that to be the case. Okay, so this is what I have, then here is what I have, and this one here as well. Now I'm going to do a few more things. Okay, look at this. I'm going to bring my figure down below and look at the point P on the spool. Okay, all right, so we look at point P on the spool, then here is what I have. I can make use of the acceleration of c for that. So one thing that I know is that at the point P, the acceleration of the cable in the tangential direction has to be the same as the acceleration of the spool. Okay, this is how it is, right? At least in that direction. So if I look at this as the tangential direction, okay, the acceleration of the point P on the cable relative to acceleration of point P on the spool in the tangential direction has to be equal to 0. Okay, this is because the spool is not slipping with respect to the cable. So this is something we can specify at the beginning of the problem if you wish. Okay, otherwise the problem cannot be solved. Okay, so this essentially means that acceleration of point P on the cable in the tangential direction is equal to acceleration of point P on the spool in the tangential direction. But we know the cable is traveling only in the tangential direction. Acceleration of P on the cable is just going to be acceleration of P in the I direction. So there is not much to it, right? So that we already know. And so here is what I'm going to do. So this essentially tells me that if I can find acceleration of P on the spool, I'm going to use this to say, okay, this is acceleration of C, and then this is going to be alpha S cross R from C to P, omega square times R from C to P, then all the relative terms which vanish for us. Excuse me. Okay, I'm going to get rid of this. I'm going to get rid of this as well. Do the substitutions. Acceleration of P on the spool will have both the components. Okay, so this is going to be acceleration of P on the spool in the I direction, or the X direction if you want to call it that way. And this is acceleration of P on the spool in the Y direction. This is equal to acceleration of C, which was 0I, and then we had R omega S square in the J direction. Okay, omega S square in the J direction, and then I'm going to have minus alpha spool K crossed with the position vector sitting at the point C, looking at the point P, is going to be R plus rho times J, and then minus omega square of the spool times R plus rho in the J direction. Which means if I look at the I terms, if I look at the J terms, P on the spool in the X direction is going to be, only term in the I direction is the K cross J, which is minus I, minus and minus becomes a plus. So this is R plus rho times alpha of the spool. If I do this in the Y direction, then I will end up getting this to be R omega S square, and then minus omega square S, and then R and rho cancels off. So this is just going to end up being rho times omega S square. Okay, so which tells me acceleration of point P on the spool is R plus rho alpha S in the I direction. Okay, and then I'm going to end up with a negative sign here because this minus omega square S times R plus rho. Okay, minus rho times omega S square in the J direction. Okay, why am I doing this is because this will tell me something about the acceleration of the point P on the cable. Okay, but we know the acceleration of point P on the cable in the tangential direction is equal to acceleration of point P on the spool in the tangential direction, which is the same as acceleration of point P on the spool in the X direction, or the I direction, right? This is the I direction. Okay, so which tells me that acceleration of point P on the cable, which is the same as acceleration of PC in the I direction, this is equal to R plus rho times alpha S in the I direction. Okay, where did I get that from? I'm getting it from here, and substitute that here. Okay, so which tells me the following: acceleration of P on the cable is R plus rho times alpha S. Okay, so that is an important thing. Okay, so the summary so far for the spool kinematics is the following. Okay, And these are things that you've done it in similar problems, I'm assuming, okay? But if not, then if this is the first time you see it anyway happening here, okay? So summary of spool kinematics. Let's get the spool here with all the labelings and so on. Okay, so here is that creature. Copy that and bring it down here, and then I'm going to start listing all the things that we have, okay? So first of all, acceleration of g is r times alpha s in the I direction. Then acceleration of then the velocity of point g is going to be r times omega s in the I direction, okay? Then the acceleration of point P on the cable is going to be acceleration of PC in the I direction, which is nothing but r plus rho times alpha s. Okay, this is for the cable. And one more thing you can also write, you can likewise, you can find the location of point A, okay, because it is rolling without slip. Maybe let me do that later down the line. I also need to know the displacement of point A and the displacement of the center of mass. Okay, the displacement of the center of mass is easy because it's going to be r times theta. Okay, so that's something that we can write down. So the position vector, okay, so r g, okay, that's the position vector. Okay, this is going to be xg in the I direction, yg in the j direction. Okay, so which tells me that rg is going to be xg is going to be r times theta because it is rolling without slip. Okay, so theta is the angular displacement of the disk. So let's write this down this way. Okay, let me call theta as the angular displacement of the disk. So this is going to be r times theta in the I direction, and the position with respect to a fixed observer is probably some capital R in the j direction. Okay, so let's say that the origin is situated somewhere here. Okay, this is my x-axis and my y-axis. This is my y-axis, and this is probably my x-axis, and the unit vector system is as shown here: positive x, positive y, and positive j. Okay, likewise, one can also make the look at the notion that the velocity of point A can be obtained. Okay, velocity of point A, and you can obtain this using the velocity of point C. Okay, so this is velocity of C, and let me bring all of these up so that I have some space to write it down. Okay, so this is velocity of C, omega of the spool, crossed at r from C to A, and then this relative velocity term which vanishes. Okay, so this is gone, rolling without slip, that's also gone, right? And so here I can say that velocity of A is going to be omega times r. Okay, so the distance is going to be 2 times r, right? So this is going to be 2 times r times omega s in the I direction. So things to keep in mind: this one here, then this one here, then I'm going to have the position of the center of mass, which I have written down here. Okay, so scoot this up a little bit, and let me scoot this down a little bit. Okay, and the last one that I want to underline is this creature here. So all the points of interest, we have information regarding them. Okay, so this is the summary of the spool kinematics, and we have made use of the fact that it's rolling without slip and so on. Okay, and there is roll without slip here. Okay, and the cable does not slip with respect to the spool. Okay, so cable does not slip as well. Okay, that's how you were able to obtain this acceleration of point P. Okay, all right, so this is the spool kinematics summary. Now I'm going to do the cable kinematics, cable pulley kinematics, plus the block kinematics. And once we do that, right, then all we have to do is draw the free body and kinetic diagrams and move on to completing the problem. Excuse me. So I go back and bring my main figure now. Okay, so this is a handful here, so I'm going to reduce the size a little bit and then capture this guy. So I'm going to copy that and bring it down here, and I think we're starting on a new page, which is great news always. I want to make sure that this is straight. Doesn't look too straight to me, so hang on, give me a minute. Let me reduce the size of this guy. Okay, that seems okay to me. I'm trying to rotate it so that it doesn't look non-straight. This is kind of tricky, isn't it? I'm not very successful at that, but I guess I can live with that. All right. Or maybe, sorry to make you, I don't mean to frustrate you. I think I'll just live with having only this without reducing the size. I think that seems to work better. Okay, so what do I do here? So in this situation, the fundamental idea is that the length of the cable is a constant. Okay, so total cable length is equal to a constant. Okay, and if I look at it this way, then here are the things that I can do. So I set up an origin here. Okay, so this point here is my origin, and from that point I measure the distance by which the cable is situated here. So let me call this as a X cable. Okay, and that's the location of X cable, and then from there the block as well. I can look at the length of the block here. The dimension of the block is not given to me, right, which means that I'm not too worried about its geometry. And let me call this as Y of the block. Okay, so that's the origin that I've chosen, and you can obviously see that the total length of the cable is a constant, so which means L total has to be equal to L wound length, then it's going to be XC and then YB, and I'm looking at the magnitudes only. Okay, okay, so LW is the wound length of the cable. Okay, then here is what I can do. So since the cable length is total length is a constant, if I take this and if I differentiate it, I get the following relationship. Okay, so taking time derivatives, okay, and look at magnitude only. I get the following. This is going to be LW double dot of W, and then this is going to be X double dot of C magnitude of Y double dot of B. Okay, that's the acceleration of the block. Okay, so this is the block B, as you can see. Okay, then I'm going to group the cable terms together, so which means that I'm going to group these two terms together. These are the cable terms, and this is the block term. Okay, so which means that just looking at the magnitudes only again, here is what I can say. Magnitude of the second derivative of the wound length, which is going to be changing over time, right? Because as the block moves up and down, the length of the cable is going to extend and keep increasing or decreasing. Okay, so this is depending on how the motion is going to take place. Okay, so this is LW dot and then I'm going to have X double dot C. This is equal to Y double dot of the block. X double dot C is acceleration of the cable, a point on the cable. Y double dot is the acceleration of the block. So this I can very well say is acceleration of point P on the cable, right? This is the point P. If you had noticed, this is the point P on the cable, right? This was the acceleration of, this was the center of mass G. Okay, so this is acceleration of point P on the cable, and this is going to be acceleration of the block. Okay, so this implies that we are looking at magnitudes only. Looking at magnitudes. Okay, we will account for the directions when we draw the free body and the kinetic diagrams. And the question is how to find LW dot, L double dot W. Okay. Okay, so we need to look at the spool at two time instances. Look at spool and cable at two different time instances. Okay, so here is the basic idea. Let's see. I'm going to get all of these. I guess I can make use of my figure from before. So I'm going to bring this and then clean up all of these things. Okay, so just bear with me for 1 second. And I'm going to cut this off, and a whole host of things here has to be taken care of. Okay, so we know that this is the direction of motion and so on. I'm going to cut that off, and let's let me not cut all of that off. Let me cut this off. I guess not. I just want to write this as point P on the cable because I got rid of that, and I'm going to bring it up there. I'm hoping I can. These are kind of tricky things, unnecessarily tricky probably. Okay, cut it off, and then I don't need these normal directions and so on. And last one. Okay, I'm going to cut that off. Okay, beautiful. And I don't need that either. Okay, so I'm going to be looking at two instances in time. Okay, so this is one instant in time. So let's say that here is the bit of the cable. So let me copy that and put that down here. Okay, so let's say that the point P was sitting right here. Okay, at some point in time. So at some time t1. Okay, the point P was sitting there, and then at time t2, the point P and the entire thing has rolled forward, right? So if I copy this and if I bring it down here, okay, this entire thing has moved forward, which means that the point P is now going to be somewhere else. Okay, so the point P on the cable is now going to be probably somewhere here. I don't know, right? That could be the location of point P on the cable at some point in time t2. Okay, so this is at time t2. And the basic idea is this. Okay, at time t1, if I look at the wound length and if I look at the wound length at time t2, the difference between the two wound lengths should be equal to the amount by which the point PC is ahead of the center of mass G. Okay, so if I look at this distance here is going to be measured as the following. Okay, so if I choose some kind of an origin, let's say that if I chose this as my origin here, then all of this is going to be x of g, right, which means that this distance is going to be x of pc minus x of g, or pc relative to g. Okay, so that is the distance, which means that the wound length at time t1 and t2, if I take the difference between the two, okay, so the difference between the wound length at time t2 minus the wound length at time t1, okay, so this is the difference between wound length at time t2 and time t1. Okay, this is going to end up being the following: minus L wound at T1, which I'm going to call as delta L wound. It is just XPC slash G, which is okay. And if I do the second derivative, then I end up getting the following. So this means that L double dot of W is going to be the second derivative of that quantity, which is nothing but the relative acceleration between the point P on the cable and the center of mass. Okay, so which tells me that L double dot is just going to be acceleration of PC minus the acceleration of G. Okay, so this is something that is very useful for me. Then I go ahead and continue. Okay, I go back to my equation which I had obtained earlier. Okay, so I take this equation here, copy that, and bring it down here. Okay, so we know this. So this implies that if I now substitute for L double dot of W, so I can do the following substitution, then I end up getting it as the following: acceleration of PC, acceleration of G, plus acceleration of PC is equal to acceleration of the block, the magnitudes only. Okay, so looking at only magnitudes. Okay, and then you know from earlier when we did the spool kinematics, okay, we know that acceleration of point G was r times alpha s, then acceleration of point P in the cable was r plus rho times alpha s. Okay, so we know both of these, which means that if I do the substitutions, here is what I end up getting. Okay, so APC minus AG is just going to be r plus rho times alpha s minus r times alpha s plus r plus rho times alpha s is equal to acceleration of the block, or r plus 2 rho times alpha s is equal to AB. This is the fundamental relationship between the acceleration of the block and the angular acceleration of the spool. Okay, this is an equation that we're going to be making use of very soon. This is the one that combines the motion of the two systems together. Okay, in that sense. Now the same problem, some people will also say that, okay, hey, don't think of the motion as too large, and if you think of the motion as very small, then this term 2 rho can be approximately equal to rho because of the smallness of the motion. So you don't think of the wound length of the cable and so on. But I don't like to think of it that way. I prefer to solve it the way I have posited here. Okay. Then I look at the degrees of freedom. Okay. And I think for this I need to bring down my figure once again. Okay. So let me bring that down here. So this is the main figure, as you know. Well, I guess the main figure is here. So let me bring that down. And let's write down the degrees of freedom, and then we are on our way to solving for the motion of the bodies, okay, the motion of the system. And you can obviously see that if you look at the block is just going to travel in the vertical direction. Okay, and likewise for the spool, it's going to travel in the horizontal direction. So if I come back and then put this down here, okay, then I can say the following. Okay, for the block, the degree of freedom that I'm going to talk about is just going to be in the vertical direction. Okay, so this is the origin, and I'm going to say, okay, hey, this is the position of the block y dot, and y double dot. Okay, and for the spool, we would have started off with 3 degrees of freedom. Okay, so spool, or 3 configuration coordinates. Okay, so that would be x at the center of mass, y at the center of mass, and then some theta. Okay, there will be 2 constraints. Yg is equal to r, that's a fixed height, right? And then the second constraint is that you're rolling without slip. Okay, which tells us that xg is equal to r times theta. Okay, so that is the idea of rolling without slip, which means that for the spool, the number of degrees of freedom will be 1. And we will call that as theta. And the important thing here is this. Now, the block is a vertical mass system. Okay, so the block is a vertical mass system, which means that we are going to measure this deflection y from the SEP. Okay, so that the gravity weight of the block is not going to be added onto this situation. Okay, so measure y from the SEP of the block, so that we will not need to look at the weight of the block. Okay, so that is an important thing, so which means that this is SEP for the entire system. Okay, and if that is the case, then SEP for the system, okay, if it is situated here, okay, and I'm going to say that this is the angular displacement, this is the sense of the angular displacement, positive sense is theta dot and theta double dot. Okay, so that is the positive sense, and this is once again from SEP. Okay, and you obviously know that alpha of the spool is theta double dot, omega of the spool is theta dot. Okay, so this implies that alpha of the spool is theta double dot, omega of the spool is theta dot. Okay, so that's done for the spool, and then for the block you can see that the degree of freedom is measured from the SEP, so that the weight of the block is not accounted for. And then all I have to do is just start looking at the displacement of the spring and the damping elements and so on. So let's start off with that. Okay, so the fourth step is the free body diagram of the springs and dampers. Okay, so in essence, how many degrees of freedom do we have? You know, one thing that I want to step back and see. The number of degrees of freedom is essentially going to be just 1. This is because the motion of the block is connected to the motion of the spool. So that's a statement that let me also make here. Okay, so before I go on to this one here, so we already know that r plus 2 rho times alpha of the spool is acceleration of the block. That is r plus 2 rho times theta double dot is equal to y double dot. Okay, so which means that the degree of freedom of the block is connected to the degree of freedom of the spool, which means that the total degree of freedom for system is only 1. So either theta or y of t, whichever you want to use. Okay, so that is the nice thing about it. Okay, and I'm going to use theta as the degree of freedom for the system. Okay, so the next step is to draw the free body diagram of the springs and the damping elements and so on, and those are fairly straightforward, as you know. Depending on how the positive sign convention is, the spring is going to be stretched, the spring K1 is going to be stretched, the damping element is going to be stretched, and likewise, depending on the positive sign convention for the block, the spring K2 is going to be stretched and C2 is going to be compressed. So let me draw it that way. Okay, so let's take this guy here. I'm going to slowly cut that off and bring this guy K1. Okay, so let me bring it down here. Okay, so this is K1. Let me do the same thing for the damping element as well. So I'm going to copy that and bring it down here. Okay, so this is that damping element. Then I'm going to do the same thing for this spring element as well. Okay, so cut this off, and to draw a free body diagram, copy that and paste it here, and likewise for the damper. And we're almost there. Okay, so this is the damping element, bring it down here. Okay, and let me start writing out the forces and so on. So this I'm going to call as FS1. Okay, because it's the first spring. This is also FS1. This is FD1 here, because that's the first damper. This is FD1 as well. Then this is going to be FS2. And likewise, this is going to be FS2. and FD2 lastly. Pointing this way, I guess it's going to be compressed, so I got to be careful here. This is FD2, which is going to be pushing down, okay, based on the positive sign convention of the block. Okay, so that's something to be careful about. This is FD2. Okay, so based on sign convention, as if spool rolls clockwise, the spring and dampers are going to be stretched. Will be in tension. Okay, and if the block moves down, okay, the spring attached to the block will be in tension. But the damping element, as you can see, as the block is trying to move down, is going to be compressed. Okay, so the damper on the block in compression. Okay, and then I can write down these forces Fs1 and Fs2 likewise. Okay, Fs1, because it was attached to the point on the topmost point, I know that the total displacement of that point, if the center of mass is displaced by r theta, it's going to be 2r theta. Okay, so this is going to be 2k1 r theta. Fd1, it's attached to the center of mass of the spool, so this is going to be c1 times r theta dot. Okay, then Fs2 is attached to the block, so this is going to be k2 times y, and Fd2 is going to be c2 times y dot. Excuse me. And we have the relationship between y and theta and y dot and theta dot, so we can also say that y dot is going to be r plus 2 rho times theta dot, and then y is going to be r plus 2 rho times theta. Okay, so this is based upon the assumption of small motion and the relationship between the block and the pulley. Okay, so that's something that we know. Okay, so for small motion, and based on kinematics of the spool and cable and the block, we have r plus 2 rho times theta double dot is equal to y double dot, and likewise r plus 2 rho times theta dot is equal to y dot, and r plus 2 rho times theta is equal to y. Okay, for small motion. All right, so now we come to the big deal, right? Drawing the free body and kinetic diagrams of the blocks and so on. So for that, I'm going to capture all of these guys. Okay, so I'm going to take all of these and clean them up a little bit. Okay, so I'm going to put them down here and cut that off, and let me label some points here. Okay, so we already have a label for this point. This point is called as the point A, right? And this was the point G. Let me call this point as the point E, and let me call this point as the point F. Okay, so which means that in this case, this is the point A, if you know, this is the point G. Okay, then this was the point E, and this point here was the point, I guess, F. Let's call it as the point H. Okay, because F is a kind of a bad word to use here. Bad choice of words to use here, because F is already a force, right? So this is going to be H. I'm just calling it as H. Okay, this is the block B, and then this is the spool. Now I'm going to look at drawing the free body and kinetic diagrams and so on. Okay, so I'm going to capture this spool. I'm going to copy that and bring it down here. Okay, and likewise, before I do anything of that sort, let me write down that this point is the point A, this was the point G, this was the point E, and here was the point H. Okay, now I bring the spool. Draw its free body diagram first. Okay, I'm going to clean up some of these things. I'm going to cut that off as well. I can cut that off. I know that this is row and so on. I'm going to cut the ground off and cut that off as well. So start off with the free body diagram. Now at the point A there is a spring attached, right? So which means that I'm going to have an Fs acting here. This is going to be Fs1. Then likewise I'm going to have Fd1 which is acting here. Okay, then I have the weight of the spool itself which is acting vertically down, so that's going to be marked here, and in a second I'm going to capture all these off and cut that off and cut that off as well. I can keep that there. The weight of the spool is going to be acting vertically down, acting at the center of mass. Okay, so that's going to be ms times g. Then I have the normal force at the contact, and then the friction force, and of course I have the cable tension. Okay, that is the important thing that kind of binds the two things together. Okay, so this is the cable tension, capital T. Okay, so this is going to be the free body diagram, and I'm going to draw the kinetic diagram. So this is F mu S. Okay, so this is the FBD. Kinetic diagram is fairly straightforward. I take the same thing. I guess I'm going to copy that and paste that and just bring only the things that I need actually. Okay, and I need the sign convention from the SEP. Okay, so starting from SEP, this is what I have, and then on the free body kinetic diagram, I'm going to have mass times acceleration of the center of mass. Okay, mass of the spool times acceleration of the center of mass, Ag, and then Ig times alpha. Okay, or it will be written as Ig times theta double dot. Okay, so in this case, Ig, since it's a non-homogeneous mass distribution, let's say that it's just written as Ig. Okay, so this is the free body diagram of the spool and the kinetic diagram of the spool, and likewise the free body diagram of the mass and kinetic diagram of the mass. And for that I'm going to take these two springs and dampers. I'm going to cut that off and bring that down here. Okay, so this is the situation that I have. Then I'm going to bring the mass in a second here. Okay, so we're almost there. I'm going to copy that and clean up a few things. Okay, cut that off. Well, I guess I do need it because that's a cable tension, as you know, right? I'm going to cut that off. Okay, so here are the forces. So first of all, at this point is the spring attached, so I'm going to have Fs2. Then this is the cable tension T. The gravity of the block is not going to be acting on this. Okay, so that's something that you want to notice. Okay, then I'm going to have at this point H, equal and opposite to the damping force. This is going to be Fd2. Okay, then all I have to do is copy this and paste this here. Then this is going to be its kinetic diagram. That is fairly straightforward. And based upon my sign convention, this is going to be mass of the block, acceleration of the block, which is mb times y double dot. And likewise I can say for the spool, this is the same as ms times r times theta double dot. Okay, this is the contact point C. Likewise, that is the contact point C. So free body diagram of the spool, kinetic diagram of the spool is done. Then this is the free body diagram of the mass, of the block, and the kinetic diagram of the block. And sign convention for the block, just make sure that I have that here. So starting from SCP, copy that and bring it down here. And the sign convention says that if I'm traveling this way, then things are going to be taken to be positive. Okay, all right. So then I start off with the block. Okay, so with the block, I'm going to say that sum of all the forces in the y direction for the block. Okay, this is equal to sum of all the forces in the y direction on the kinetic diagram. Okay, and let's say that things pointing up are positive, things pointing up are positive. What are all the forces? The tension T is pointing up. Okay, so tension T, and then I'm going to have Fs2, and I'm going to have Fd2. Okay, and this is going to be equal to minus mb times y double dot. Do the substitutions. Okay, so if I write down everything, then here is what I end up getting. So tension T is going to be minus mb y double dot minus fd2, which is going to be c2 times y dot minus k2 times y. Okay, so these are all the things that I have for the tension. Then I go to the spool. And you know the basic idea for doing this. What do I do in the spool? If I go and bring the free body and the kinetic diagrams, let's take this and bring it down here. Okay, so I'm going to copy that and bring it down here. I guess let me go to the next page, if that makes better sense. Okay, so let's take this guy off and bring it down here. Okay, and I'm going to clean this up. You obviously know this is the free body diagram. We know this is the kinetic diagram. So what am I going to do on the spool? I'm going to sum moments at the contact point, because I don't want the friction force to be a part of the equation of motion. So I have to sum moments at the contact point. So MC on the free body diagram is equal to MC on the kinetic diagram, counterclockwise rotations, counterclockwise rotations. What are my rotations? I'm going to have the following. Okay, so first of all, Fs1 times the distance of 2r, counterclockwise. Okay, then I'm going to have Fd1 times the distance of r. Then don't forget the tension. This is going to be minus T times r plus rho. Then I come to the kinetic diagram, which is going to be Ig theta double dot clockwise, and then minus ms times r theta double dot multiplied by r. Okay, then start rearranging the terms. Okay, so Fs1 I already know is 2k1 r theta, right, times the distance of 2r. Fd1 we knew it to be c1 times r theta dot times r minus t r plus rho. This is equal to minus theta double dot times Ig plus ms times r square. One thing I wanted to I forgot to write down here is mass of the block. I did write it down. Okay, then I know from the block that the tension is written this way. Okay, so this is from the block, we already know. From the block analysis, so I'm going to substitute for the tension then. Okay, so substitute for the tension, put it down on there, and if I rearrange the terms, here is what I'm going to end up getting, and the entire system is moving due to some initial conditions. Okay, that's something that you can make a note of. So this is 2 times 2, and then that's 4r square. So that's 4r square times k1 times theta. Then I'm going to have c1 times r square theta dot, and then r plus rho times minus of the tension. So that's going to be mb times y double dot, c2 times y dot, k2 times y. This is equal to minus theta double dot times Ig plus mr square, mass of the spool ms. start rearranging the terms and write it down. Okay, so here is what I'm going to end up getting. So this is theta double dot ig plus ms r square. And then look at this, y double dot is going to be the following, right? So this is going to be, this is a plus sign, I'm sorry, because all of them become positive because the tension had a negative sign accompanying it, and that was minus mb, minus c2, and minus k2, so they all become positive. So this is plus mb times r plus rho, and y double dot is r plus 2 rho times alpha of the spool, which is theta double dot. Then I'm going to have c2 times r plus rho, r plus 2 rho times theta dot. Okay, and I'm going to put a big bracket here. Then I'm going to have k2, which is going to be plus r plus rho, r plus 2 rho times theta, and then I'm going to have c1 r square theta dot, and then I'm going to have 4 k1 r square theta. All of that put together is equal to 0, or combine the terms. I'm going to have the following. Okay, so ig plus mr square, mass of the spool, that's one term that I have, and then this is going to be r plus rho, r plus 2 rho theta double dot. That's the first thing. Then collect all the terms containing theta dot. Okay, so I'm going to have r plus rho, r plus 2 rho plus r square times c1 theta dot, and I'm going to make enough space to bring all of them in here. Okay, so let's see if I can bring the spring as well, so that I can write the whole equation of motion in one line. And then r plus rho, r plus 2 rho, 4 k1, and that's going to be, I forgot a c2 here, so apologies for that. There's going to be c2 here and k2 here, so this is going to be k2. Okay, and there's going to be a c2 here. Okay, and then there's going to be a k2 here. Okay, sorry about that. And that's k2, and multiplied by theta is equal to 0. Okay, so this is the whole equation of motion. Okay, and there's an r square missing, I'm sorry. So let's make sure everything is captured here. And there's 4k1 r square. Okay, so this is the whole equation of motion, and this can be cast in the standard form, okay, by doing the following. Okay, so if I copy that and I bring it down here, so this is the equation of motion for the entire system. Okay, we can cast it in the standard form, right, in the standard form, which is 1 by omega n square times theta double dot, and then 2 zeta by omega n theta dot, and then theta is equal to 0, where omega n square is going to be the following. It's going to be that big term there, r plus rho, r plus 2 rho, k2, 4 k1 r square. Okay, and all of this divided by ig plus m spool r square plus r plus rho times r plus 2 rho. Okay, likewise you can also write zeta as the following. So zeta is c by 2 m omega n, okay, where c is equivalent to the following term. This is the equivalence sign, r plus rho, r plus 2 rho times c2, and then r square c1. Okay, and then mass m is equivalent to this bottom term that you have here. Okay, copy that and paste that here. So these are the equivalent terms. Okay, And so this is the fundamental idea here. So how do I write these important terms that are system properties? Okay, the natural frequency and the damping ratio. All right. So this is the problem that I have for you, and please do go back and look at the different steps involved in this particular problem. We started off with spool kinematics, then we did cable kinematics, then we did the free body and the kinetic diagrams of the springs. Before that, we set up the coordinate positive sign conventions and the degrees of freedom, and then lastly we wrote the equation of motion. All right. Thank you very much for your patience, and take care of yourselves and stay safe, please. Bye bye.